be out of the derivative, d by dt of A, negative nb, and then you have here, this is pi r squared, and then pi r squared. So then you have here negative nb 2 pi, the derivative of this is going to be what? 2 pi r dr dt. So let's say the radius changes as a function, something like this. So if we go to the simulation, so I'm going to try to mimic a problem that resembles this situation. I have a magnet inside of it. So then I'm going to start with the radius small, like this. So the radius here is about about 15 centimeters. So initial radius is 15 centimeters. So then I am now increasing the radius all the way to 100%. So this radius is 35 centimeters. So let's say I go back and forth in a second. So the period of the motion is 1 second. Yeah, that's pretty doable. So the period of the motion is 1 second. So I start with the initial radius, and then the radius gets big, and then the radius gets small. Radius gets big, radius gets small. You see? So I'm changing the r. So what kind of function would that be? R starts at 15, goes to 35, comes back. It's almost like this kind of function. 15 all the way to 35. And it repeats every 1 second. So like this kind of up, down. Let's see here, the average values. So the average value is 25 with an amplitude of 10. Average value is 25 with an amplitude of 10. So we could say negative 10 cosine of omega t plus 25. I'm making a function for it. Yeah, that should work. And then omega is equal to 2 pi over the period. Aha! Good for me. I got the equation for it. R of t. So I came up with a function to describe what I'm doing. I'm starting at 15, making it grow to 35, and then coming back to 15 in 1 second. So it looks like this, and then back to 35, and then back to 15. So negative 10 cosine of, since it's 1 second, it's just 2 pi t plus 25. So if you put t as 0, you're going to get negative 10 plus 25, 15. Yep. And then if you put t as 1, you're going to get cosine of 2 pi. Yeah, it's going to be 1. So if you put half a second, what should you get? T is a half a second. you should get the 35, right? So half a second, 2 pi times half, that's gonna be cosine of pi -1, 10 plus 25, yep, 35, got it. So right on the spot, I came up with a equation for it. So now we could say the general equation for the EMF induced is the number of loops times the B field times the 2 pi r, which is this function, times dr dt. Okay? So then what do we get here? Let's continue on another page. Okay, so you're going to get EMF is negative NB 2 pi r dr dt. R is going to be negative 10 cosine of omega t, or cosine of 2 pi t, because you already determined the omega, 2 pi t plus 25, right? And then dr dt is going to be the derivative of that function. So the r of t function was negative 10 cosine of 2 pi t plus 25. Oh no, these were actually let's see, 15. They were actually 1.5 centimeters and 2.5 centimeters. Okay, so it should be 1.0 centimeter and 2.5 centimeter. So I'm doing here negative NB 2 pi 1.0 2.5, then dr dt was the derivative of this. So the derivative of cosine is negative sine. So then that's going to cancel this -1. So then sine of 2 pi t times the derivative of the inside, which is 2 pi. Oh, so the EMF that's induced is actually some kind of a trig function itself, right? It looks like this. So let's see here, what's N? N is 2 loops. What's the B field? Well, since I'm placing the magnet inside, the B field will be equal to its value when we were inside. What was that? It was in Gauss, or 42 Gauss from the previous problem, right? So 42 times 10 to the -4. That was the B field. So I'm keeping the B field the same. Then you got here 2 pi. Oh, then you got 2 pi squared. You got another 2 pi from here, and then another 2 pi from the derivative. So 2 pi squared. So negative cosine 2 pi t plus 2.5 sine of 2 pi t. And that's the EMF induced, right? So it's kind of the EMF induced is itself a trig function. Okay, so let's see here. You see, if I go like this, so if I go like this, so you should be seeing this thing go like back, forth, back, forth. So essentially I've created an AC voltage source, you see? It's gonna go back and forth like an AC source. Wolfram, just bring it all on, baby. So the voltage is function, EMF is gonna be -2 times 42, and it's a Gauss, times 10 to the power negative 4 times 2 pi squared times sine of 2 pi t negative cosine of 2 pi t plus 2.5 centimeters. So then if it's 2.5 centimeters, I'm going to have to add a times 10 to the minus 2. Okay, so I added, because they're centimeters, so because these were centimeters, I added a 10 to the minus 2. So this is or 2 pi. Well, you know what? It's 10 to the minus 4 because this is a centimeter and this is another centimeter. It's the r dr dt. So then that would be, this is centimeter and centimeter. So I have to multiply it by 10 to the minus 4. Oh, so it's going to be really small. So 10 to the minus 4 because of the b, and then 10 to the minus 4 because of the centimeter. So the EMF induced is going to be really small. 10 to the minus 4. Let's zoom in, because the numbers are going to be. Zoom out. Well, since it's so small, let's just take the 10 to the minus 8 outside. Oh, okay, this is nice. So just remember that there's an extra 10 to the minus 4 to whatever number it's showing here. So now we could figure out, so at t equals to 0, the voltage induced is 0. But then as soon as I start changing the radius, I'm starting to induce a voltage. Negative voltage means what? Clockwise, as seen from the right side with your eye. You see negative voltage. So then at 1 second, it comes back to the normal. So the maximum voltage induced is 0.886. You see the magnitude, the 0.886, and then over here, it's another 0.886. So 0.886 is the maximum. I'm looking at the y-axis. Okay. So the maximum voltage induced, the graph looks like this. So first, the voltage goes negative, then until a half a second, and then after half a second, it goes positive. And then the values of these numbers is 0.886, but then it has an extra 10 to the minus 4. So that would be what? 0.0886 millivolts. Yep, 0.0886. So if I go to the left, I can make that 0.0886 millivolts. That's the maximum voltage created. Can we make sense of the clockwiseness and the counterclockwiseness? Why is there voltage first producing a clockwise current? Well, I have the magnet sitting like that. And first, the radius is getting large, right? During the first half of the cycle. The radius is getting large. So then what's happening to the flux? The flux it's kind of equivalent to me putting in the magnet. Here, I'm not actually putting in the magnet. I'm just increasing the radius, right? So what's going to happen? It should produce a current that's like this, as viewed from the right side. It should produce a current that's like that to fight against the B field, you see. By increasing the radius, I'm increasing the flux that's to the right. So then that current should be registered as a negative current. Yep, makes sense. But then when the radius starts getting down, oh no, then it starts saying, I'm going to fight against it. You're decreasing it. So then it produces a positive voltage, which means the current reverses direction. So first this way, then this way.